Hello ladies and gentlemen, my name is Günster and I'm very happy that I can report here on this joint ACerS-ECerS Symposium, and I will talk about dense powder beds for the additive manufacturing of ceramics. It's a topic we basically follow up since 20 years, and I will report here on our outcome in this field from the last 5 years. This is the agenda of my presentation. I will start with a short introduction in powder-based additive manufacturing, and then I will come to the layer-wise slurry deposition, which is basically our working horse. This 3D printing of ceramics, we do that also since about 20 years. And then I will come to a more recent development, which we call gas flow assisted powder deposition. Okay, let's start with the introduction. Shown here is a schematic of the selective laser sintering process. In this process, a dry powder is spread layer by layer on a building platform, and you use a laser system which consists of a laser and a scan head, which focus the laser spot and moves it on the surface of the powder bed, and you consolidate locally the powder with this laser spot. This process was developed by UT Texas Austin end of the 80s of the last century. Another powder-based process is a 3D printing process which was developed by MIT. In the beginning of the 90s, it's basically the same. You have a dry powder, you spread it layer by layer on a building platform. Of course, you can use different spreading tools. We have a roller, recoater here, it can be a blade and a shaker system, whatever. And then when you have deposited the layers, you consolidate the powder by injecting drops of a binder into the powder bed. So coming to one of the major problems of the powder-based additive manufacturing for ceramics is that when you use a dry powder, the packing density of the powder bed is not very high. And the reason is quite obvious. There's only one force which is acting to consolidate the powder. It's a gravitational force. You may activate the powder by some shaker or roller, but this force, the gravitational force, scales with the volume of the particles. And when the particles get smaller, the force gets smaller, and the particle-particle interaction itself, it's not getting smaller, it's not scaling directly with the particle size. And so from a certain particle size, the gravitational force acting on the particles will be smaller than the particle-particle interaction. And then it's the point definitely where the particles start not to pack well anymore. So why do we like powder-based additive manufacturing? So the specific merits of powder-based additive manufacturing are that it's a robust process and it's easy to scale up. So we see a machine which has a size of 2 meters times 2 meters times 2 meters, and you can use a relatively simple setup. This machine is located at Manera in Rovigo, Italy. So you can check here under this address, this company. That's the CEO, Antonino Italiano. We collaborate with him in an EU project. And the interesting thing here with this machine is that it piles up this huge amount of powder directly on the ground, and you build up the powder bed here on the ground. So easy upscale, and you can use a wide range of feedstocks. It's not only for this machine, it's generally for powder-based additive manufacturing. There's another function which is very important of the powder bed, that it's supporting the printed structure. You can see here this bench, and this large overhang here is supported by the powder. Here it's already taken out of the powder bed, but you can easily imagine that this powder here supports in the printing process such overhangs. So what is the function of the powder bed? First, what I already said, it supports the printed structure. Then the microstructure of the powder bed basically translates into the microstructure of the part. This means to have an advanced ceramic or a dense sinterable ceramic, you should use particles which pack well, so you should achieve maximum packing density, and of course, to have the right sintering activity, you should use fine powders up to sub-micron powders. When you do additive manufacturing of ceramics, it's always worth having a look at the ceramic powder process chain. It starts with the raw materials processing, goes into the forming, and after the forming, you have the sintering step. So from the raw materials processing, you get ceramic intermediate products like powder, slurries, paste. In the forming process, you generate basically the shape of your part, and what you produce is a powder compact with a maximum packing density of the particles, so that it can be sintered and the sintering process finally to a part with a density of nearly 100%. That's what you usually aim when you want to achieve the superior physical-chemical properties of an advanced ceramics. When we do powder-based 3D printing, generally we need a flowable powder, and this flowable powder has a particle size typically larger than 20 microns. And with the use of such a powder, your powder compact, this part here, which you print, will have a packing density of the particles of about 40% theoretical density. And the sintered body, of course, with this low packing density and with this large particle size will not be dense. So it will be significantly below 100% theoretical density. So coming to solving these problems, we have developed a process which is called layer-wise slurry deposition. The layer-wise slurry deposition is a process where we use, instead of a dry powder, a ceramic slip. It's a water-based slip, so we don't want to deal with organics. So we mix the ceramic powder with water, with some additives to a classical slip casting slip, and then the layers are deposited by means of a doctor blade. Each individual layer is dried, and then you can use a laser to consolidate the powder locally. So this is like a green body, like a slip cast green body, layer by layer. And then you consolidate the powder by means of a laser or by a printhead. And then different to the standard process, to the powder-based process, is that you need to wash out the part, because this material here is like a green body, what I said already, and this green body is relatively dense. You have a density of about 60% here, and you cannot simply take the part out of the powder bed, so you need to wash out the part out from the powder bed. The schematic here shows the layer-wise slurry deposition process more in detail, and this is the slurry which is spread by a doctor blade over the dried previous deposited layer, and the slip which is deposited is in a slip casting process desiccated and forms a cast on this layer. So this ensures that you have a high packing density and that the connection between the layers is good. So it's a mix of tape casting and slip casting, basically. Now we combine the layer-wise slurry deposition with the selective laser sintering process. This is how a laser sintered part from the LSD process looks like. You see the powder bed has a high density, it's relatively tough, like a green body. Depends, of course, on the binder and the slurry. And here you see two espresso cups which are laser sintered into this block. The block consists of 360 layers of each 100 micrometer thickness. In order to release the parts out of this green body block, you place it into water and you start to wash out the parts. Here you can see the washing process more in progress. You see the nice surface finish of the cup. Here's the laser sintered body. That's the surface towards the laser. It is more shiny. You see a temperature difference here from the outer, so as wider it is, as a higher temperature it has reached. And this is one disadvantage of the laser sintering process. It's anyways not ready to use, and you have a rather inhomogeneous structure. The density of these bodies is not bad. It's in the range after post-sintering of 90%, but you have a quite large residual pores in this body. Nonetheless, you can biscuit fire them. That's a S laser sintered body. This is a body biscuit fired, and you can glaze them, and the haptics is quite nice. Here's another example. It's a porcelain cup made out of 1,000 layers, each 100 micrometer thick. And here are some specs from the process. So we used a 100 watt continuous wave fiber laser emitting at a wavelength of 1 micron. And the laser was typically operated at a power output of 20 to 30 watts. 1,000 layers, what I already said, 100 micrometer thick. The total energy consumption of the laser during the entire sintering process is 5 kilowatt hours, so that's not a lot. Problem is the processing time and especially the laser on time. The laser sequentially sinters layer by layer. There's not much you can do to reduce this 20 hours. Maybe you can use multiple laser spots, but that's it already. It's the current state of the art. So what you would need is a more advanced technology to illuminate maybe an entire cross-section or an entire layer at once. But at the moment, I don't see that inside. Alternatively to the laser sintering, we use the binder jetting to consolidate the powder. I introduced that already. And the binder jetting results also in very nice parts. The parts are now not sintered. You have just a binder to consolidate the structure. It's the same like with the laser sintering. You need to wash out the parts. Here are shown porcelain parts. But the speed is much higher because multiple jets from the printhead can address an entire area of the part, and you move the printhead multiple times or only one time over the part, and this is speeding up the process significantly. Here seen is also the result from the 3D printing process. It was a giveaway which we made for Christmas. It's a little elf town, and you can see here that the resolution is quite nice. I will not say it's in the 100 micrometer range, but minimum in the 200 micrometer range. And this is a porcelain part made from a porcelain from KPM from Berlin. What are the properties of the 3D printed and sintered parts? For porcelain, shown here. So we test with a ball on 3 balls test according to Robert Danzer's approach. And the nice thing is you can use here small tablets which we printed, and we printed them in different orientation so that the maximum stress is here perpendicular to the layers, and here it's in plane with the layers. So that's a YZ and that's a XY direction. And when we compare the strengths of the different directions, you see here a Weibull statistics plot, and you can see here's a nice scatter from 30 samples. And we have the XY, the XZ, the YZ directions, and the reference from a slipcast standard sample. Shown here are the Weibull characteristic strengths and the Weibull modulus from different samples. These are 3D printed samples with 3 orientations. This is the most critical one with the layers perpendicular to the maximum stress. And this is a slipcast sample, and these are suppressed samples. For each we have manufactured 30 samples and tested 30 samples. And an average, you see here, the Weibull characteristic strength is in the range of 70 megapascal for all samples, especially for the critical orientation. The Weibull modulus is also similar, except of this orientation, which is actually not critical. But we have printed all 90 samples for this 3 test series here in one block, and maybe this corner, they have been here, this ensemble of 30 samples have been in the corner of the block, which was not so favorable for the process. Another material system which we use for LSD-based 3D printing is silicon carbide. So you see here a sample which is 3D printed and silicon infiltrated during sintering. It's a collaboration with a Kyocera company. Here's a sample which shows the resolution with the different feature types, and also here it's confirmed that the resolution of the process is basically 200 microns. Also for silicon carbide we have tested the mechanical strength of the samples with a balls on 3-ball test. 30 samples each have been tested, and you see here the most less favored orientation with layers perpendicular to the maximum stress, the YZ direction, and you see there's a nice homogeneous Weibull plot. The strength, the average strength of the LST printed parts is still inferior to the industrial manufactured ones. Mostly that's due to the fact that the density of the green body is even higher in the LSD print process, and there was a problem with the infiltration of silicon. Nonetheless, this is not an optimized result, that's a kind of first shot. You see that these values, the biaxial strengths, are not that bad. Also, when you look here into the graph, you see that we have a maximum values comparable to the industrial samples. The scatter is significantly higher from the LSD printed samples at the moment. In order to improve the printing speed of the LSD-based binder jetting process, we currently work on a new technology. So we have a continuous deposition process. So instead of depositing layer by layer, depositing, drying, and then printing, we have a continuous process. It's running on a disk. So to a certain width, we deposit the slip here in a continuous way. We dry continuously and we print continuously. And we have a little startup which is translating this process into a process idea, so to say, into a technology. And here we are showing first results. You see here the continuous deposition and the parts printed into the powder bed continuously. So we printed here 7 of these honeycomb structures from alumina. And I think the most striking value is that we can print now in 1 hour a volume of 1.3 liters about. So this is a huge improvement. So the startup is called Ceramic. So if some investor is interested, then contact Jörg Lüchtenburg. Finally, I will come to the gas flow assisted powder deposition process, which is a process which is also to improve the packing density of dry powders during deposition. The gas flow assisted powder deposition process was envisioned to stabilize parts in the 3D printing process. Why is this necessary? I said the powder supports the part in the powder bed, but the powder is rather loose, and when we print our standard ceramics, bioceramics, coarse-grained powders in a fraction from 60 micron to 100 microns, then we get a packing density typically of 40%, so the powder bed is not very tough. And when you deposit a new layer, sometimes the recoater touches the part and displaces the part in the powder bed. Therefore, we typically print the parts with a support structure. The support structure is not nice, it needs to be removed. Typically that's a process which comes after the printing and takes a lot of time. And when you don't use the support structures, then you have this shift in the parts typically. The gas flow assisted powder deposition process stabilizes the powder by drawing gas through the powder. So you have a pressure difference here from the top layer of the powder to the bottom. So the bottom here is a porous plate, that's a building plate. And by means of a vacuum pump, you're drawing the gas through the powder bed. The process is rather easy to implement into older machines. So here is shown a retrofit for X1 printer. You simply take the dense plate and replace it by a metal filter plate. You have a little manifold, you connect the vacuum hose to that manifold, and then you have an adapter to the mechanics. So what are the specific merits of the gas flow assisted powder deposition? So the gas flow improves the density during deposition. We measured that, I will show that later. So it facilitates the use of more finer powders because there's an additional force now acting on the powders, not only the gravitational force, but also the gas flow. The gas flow stabilizes the powder bed, so we don't need support structures anymore. And one important point also, it keeps the printhead clean because there are very few particles now emitted from the powder bed back to the printhead. Here you see the powder bed pushed out of the printer. Here are the printed parts. They're brownish because there's a heat treatment for cross-linking the printer, which is not completely homogeneous. But you already see that the packing density is high because you see that this is not flowing. It's a flowable powder, and generally it flows. But due to the high packing, it's coming out as a block. And then you can see that we scatter now the parts into the powder bed. There's no support structure anymore, and the parts look nice. So here is the effect shown to the densification of the powder. So we used two powder fractions, one coarse grain powder and one more fine powder. And this 17 micron alumina powder is typically not flowing well. So this is our standard glass ceramic, bioceramic powder, which has a good flowability. And when you simply look at the free settled density of the different powders, here you have the good flowable powder with over 40% free settled density, and the poor flowability with 30%. And then you tap the box, so to say, where you have poured in the powder. You improve the packing density, of course, here up to 50% and here 43%. The ratio gives you a Hausner ratio, which is a reasonable well measure for the flowability of a powder, and a low Hausner ratio near to 1 is indicated for good flowability. That's a typical poor flowing powder. And when you apply the gas flow, we measured the density of the powder bed of 50 layers. And then you see without gas flow, with a good flowable powder, you reach intermediate density in between those. But with a poor flowable powder, it's even inferior to the free settled density. And with the gas flow, you have a packing density similar to the tap density. The improvement is not huge here. The particles are large, but with the fine particles, you have a quite nice improvement, and this is close really to the tap density of the powder. This graph shows again which forces are acting on particles during powder deposition, and also in the gas flow assisted powder deposition, we have an additional force from the gas flow field, additional to the gravitational force, and this force directs the particles favorably to the hollow sides, not to the on-top sides, which are associated to a good packing of the powders. I would like to thank you for your attention. I hope you stay in good health, and my special thanks are also to the organizers of this special symposium. Thank you.